Okay, so welcome to the Calculus 1 review. I'm Professor Miller, and the goal for today is to just quickly go through the key ideas in Calculus 1. So Calculus 1 is mostly differentiation. It's not entirely, there's a little bit of integration depending on who teaches it. So if there are questions, feel free to put them in the chat or just ask. A lot of it comes down to knowing algebra. So there's a lot of algebra prerequisites, and I will make some handouts available if anybody wants to practice their algebra, but you really need a solid foundation. So it turns out one of the most useful things to do in mathematics is to do nothing. And there are two good ways to do nothing. You can multiply by 1, and you can add 0. And it turns out if you can find good ways to do this, you can often take an expression and rewrite it in a way that's more illuminating. And so much of what's going on, if somebody shows you step by step by step what's going on, you can follow it, but it's how do they ever think to come up with that? A lot of it is practice. The more times you do things, the more you start to get a sense of what it's like. I like to describe it as, it's baby mathematics. You have a baby, the baby is screaming. Why is the baby screaming? Does the baby want to be held? Does the baby want to be burped? Does the baby want food? Does the baby want the Red Sox to do better? You start going through your checklist. And after a while, you recognize that's the hungry scream. That's the I need a new diaper scream. And you don't have to go through the whole list. You have enough intuition that you can quickly look at it. For so many things, we need to be able to find what's the right way to look at the algebra to see what's going on. So one of the big ingredients that we're going to need is the binomial theorem. And that says if n is a positive integer, then x plus y to the n is x to the n plus n choose 1, x to the n, y to the n minus 1, plus n choose 2. Oh, sorry, this should be not y to the n minus 1. Sorry, I have the wrong exponents. It should be x to the n minus 1, y to the first, plus x to the n minus 2, y squared, plus dot dot dot, plus n choose 1. So n choose n minus 1, x, y to the n minus 1, plus y to the n. And really what's going on here is 1 is equal to n choose 0 in this spot, and n choose n in this spot. You might have seen this through Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. This is the coefficients of expanding out x plus y cubed. This is expanding out x plus y squared, and so on. And n choose k, this is the number of ways of choosing k objects from n when order doesn't matter. This is n factorial over k factorial. That's a bad factorial. K factorial, n minus k factorial. And here, m factorial is m minus 1, 3 times 2 times 1. And we define 0 factorial to be 1. So m factorial is the number of ways to order m objects when order matters. And a la Seinfeld, we say 0 factorial is 1. There is one way of doing nothing. How many ways can you order no elements? There's one way to do nothing. If you think about expanding x plus y to the n, well, each term is going to have some number of x's and some number of y's. If I have x plus y to the 5th, then however many x's and y's I have in a given term should add up to 5. So if I have x twice, I have y 3 times. And that's why you have coefficients like n choose 1, n choose 2, etc. If I want to have exactly 2 x's, I choose 2 of the n factors of x plus y to give me an x. And then the remaining n minus 2 give me the y's. Now, when you look at this, it's written as n choose 2. You could, if you want, write this as n choose 2 times n minus 2 choose n minus 2. We choose 2 of the factors to be x, and then we choose the remaining n minus 2 to be y. Well, how many ways are there to choose n minus 2 objects from n minus 2 objects? There's one way. You just take them all. And this goes back to what we said on the last slide. So much of mathematics is about doing nothing. You're multiplying by 1, adding 0. And n choose n, or n minus 2 choose n minus 2, that's just 1. So we often don't put those factors in, which can make it a little bit hard to see what's going on. So why do we care so much about the binomial theorem? We're going to use that to find the derivative of one of the most basic functions possible. So the first should be the notion of what is the derivative. So the derivative, it studies the rates of change. So I always like to have in my mind some kind of picture. So maybe the horizontal axis is time, the vertical axis is distance. And I have some function that tells me, you give me a moment in time, and we often use x, even though we probably should use t for time, and that will tell me how far I've traveled. Well, if I know how far I've traveled at one moment in time, and I know how far I've traveled at another moment in time, I can then say, oh, okay, well, in this intervening time, I know how far I've moved. So for instance, maybe I have some point A, and I have another point A plus h a little bit later. And I can see over here, this is the change in time, which is h. And then over here, I can look at the change in distance. And so if I look at the change in distance over the change in time, that will give me my average speed. And so let's just zoom in on that. It's fun to have all these different colors that we can use. So let's imagine, here is my time axis, and here's my curve. Let's say something like this. Here's my time A, and here's my time A plus h. And so what I can do is I can calculate the average speed from A to A plus h. So average speed from A to A plus h is f of A plus h minus f of A over A plus h minus a. So this is the change in distance over the change in time. So we're doing change in distance over change in time. Well, the bottom is just going to be h. So this is just f of A plus h minus f of A over h. And what we can then do is we can take the limit as h gets closer and closer to 0. So when we take the limit as h gets closer and closer to 0, we never have h actually equal to 0. We always have it as a small amount arbitrarily close, but not actually equal to 0. So then we say the derivative at a, which we'll write f prime of a, is the limit as h goes to 0 of f of A plus h minus f of A over h. And sometimes it's actually a little bit better to write this as the limit as x approaches A of f of x minus f of A over x minus A. And they're really equivalent. You can look at one or the other. So the idea is that if we take smaller and smaller periods of time, the average speed should be closer and closer and closer to the instantaneous speed. If you're driving from Boston to DC and you want to figure out what is your instantaneous speed at one moment, well, if you try to estimate your instantaneous speed by looking at the entire trip, that's a terrible idea. You're going to have major traffic as in your cities. You could have construction. But if you look at where you are and then where you are, half a second later, hopefully your speed has not changed too greatly in half a second, and that how far you've traveled should be a pretty good estimate. So when we look at what's going on in the limit, as the line gets closer and closer and closer, so here's our curve again, f of x, here's our point A, and this line over here is called the tangent line. And this is obtained by taking the limit as we take our points, A plus h getting closer and closer and closer to the point A. And the slope of that line gives us the instantaneous speed. So the first big thing is, f prime of x is the limit as h goes to 0, f of x plus h minus f of x over h. So if this limit exists, we call that the derivative. Why is this hard to do? Oh, wait, it doesn't seem like it's sharing the screen anymore. Let me share the screen. Hopefully it's been recording that the iPad. Just in case it hasn't been recording, let me just quickly go back and show the previous slide. So we had just talked about the binomial theorem and why it was so important. At least the slides are going to be available online. We talked about the derivative and trying to find the instantaneous speed by looking at the average speed over small and smaller periods of time. We said that the change in distance over change in time will be f of a plus h minus f of a over h. And then the tangent line is going to be the line whose slope is that instantaneous rate of change, if that exists. Now, the way you would love to calculate the limit is you'd love to say the limit of a quotient is the quotient of the limits. The problem is, as h goes to 0, the denominator h goes to 0, and the numerator goes to 0, so we have 0 over 0. And 0 over 0 is undefined. So that means we have to be a little bit more careful. So what we want to do is we want to start with functions whose derivatives we can hopefully compute. So again, f prime of x is the limit as h goes to 0, f of x plus h minus f of x over h. And the goal is you always want to start with the easiest function you can. So what's the easiest function you can think of to try to find the derivative? Okay, something even easier than a linear function. Constant. So the first case, let's take f of x equals c. We get f prime of x is the limit as h goes to 0 of c minus c over h, which is the limit as h goes to 0 of 0 over h. And now what we know is h is not 0. It's the limit as h tends to 0. Well, 0 over h is just 0. And so what is the limit of 0? It's just 0. So now the next thing we do is we could do a linear function. I'm going to just keep our functions as pure. And later we'll prove the derivative of a sum is the sum of the derivatives. So if we can understand the derivative of just x squared, x cubed, we can understand their sums. Then we would prove that if I multiply by a constant, I just change my derivative by that constant. And so the idea, and this is a really key idea in mathematics, is you try to break things up into as simple of a case as possible and then piece it together. So the next is, f of x equals x. We would get f prime of x is the limit as h goes to 0. We'd have x plus h minus x over h, which is just the limit as h goes to 0 of h over h. Oh, well, what's h over h? That's just 1. And so the limit as h goes to 0 of 1 is just going to be 1. This kind of makes sense because if you think about the plot, your distance is basically the same as your time. They're in different units, maybe distance is in meters, time is in seconds. But it seems very reasonable that my speed should be 1 meter per second. Now let's do something a little bit more interesting. Let's do f of x is x squared. So we get f prime of x is the limit as h goes to 0 of x plus h squared minus x squared over h. And now for the first time, we actually have to do a little bit of work. And so we want the limit as h goes to 0. Well, x plus h squared is going to be x squared plus 2xh plus h squared. And that's just using the binomial theorem, minus x squared over h. So we see the x squared cancels with the negative x squared. We have 2xh plus h squared. We can divide through by h. And this is going to be the same as the limit as h goes to 0 of 2x plus h. Well, as h goes to 0, 2x plus h is just going to go to 2x. And we can see that it may not be pleasant, but it looks like the algebra should be doable for any integer n. That if I have x squared, x cubed, x to the fourth, I can keep doing this. And the key thing that all we really need is we need x plus h to the n is x to the n plus n x to the n minus 1 h plus crap with h squared and higher. We actually know what the crap is. The binomial theorem tells us. But all we need to know is that when you expand x plus h to the n, it starts off as x to the n. I choose x from each one. I have no choice. Then how can I get an x to the n minus 1h? I choose one of the n factors to be h. And then every other term is going to have at least an h squared. So if I look at x plus h to the n minus x to the n over h, the x to the n cancels with a negative x to the n. The n x to the n minus 1 over h, the h kills that. So that's going to be n x to the n minus 1 plus crap with h and higher. So now, as h goes to 0, it goes to n x to the n minus 1. And so we get, if f of x is x to the n, then f prime of x is n x to the n minus 1. N is a positive integer. It turns out it's still true if r is a real number. The proof I gave only works if n is a positive integer. This is supposed to just be the 50-minute introduction to all of Calc 1, so I'm not going to go through the technicalities, but this is where a lot of high school classes lie a little bit. And they don't talk that you can't use the standard proof here because this proof is using the binomial theorem, which assumes that we have an integer. Notation is extremely important. So I know there is a reason why cosecant goes with 1 over sine and secant goes with 1 over cosine. I hate it. I would love to put the cos together. There's no way we're changing that. So you always want to think about what is your notation. So we've been writing for the derivative, f prime of x. We sometimes write df dx. If you only have one variable, the prime is not a bad notation. When you do multivariable calculus and you have several variables, you can actually talk about, let's hold all the variables but one fixed. And I might say, I want the derivative with respect to x, but not with respect to y. Or maybe you want to let multiple variables move, but not all of them. And so you want notation that generalizes. So right now, the prime notation is fine, but as you go further, the df dx is actually very good notation. There's also more than one way to write the derivative. We've been writing the derivative as the limit as h goes to 0 of f of x plus h minus f of x over h. A better way is to look at the limit as x goes to a of f of x minus f of a minus f prime of a x minus a over x minus a. This generalizes better for Calc 3. And so why is this better? Well, if you think about what's going on, and this leads us into Taylor series, if you had to approximate your function, you might say, well, look, I want to approximate f of x. If I know where I am at time a, why don't I just say for all eternity, that's where I am? F of x is just f of a. Well, that's a little bit silly to say that I never move. If that's the case, your life would be very boring. So why don't I put in a little bit more? What if I know my instantaneous speed at time A? I know not only where am I, but how fast I'm traveling. So then if I wanted to know where would I be at time X, I could say, well, what if my speed was always my speed at time A, and then I multiply by the elapsed time? And so if I do that, this should be a pretty good approximation. And this is essentially, the tangent line approximation. And if you look at what we're doing in this other definition, we're subtracting off where we are from where we would have been if our speed were constant. So above is where we are minus where if speed constant. That's what's really going on here in the numerator. All right. So the next thing you do in calculus is you start proving different derivatives. So we have a function and we have its derivative. And we want the most expansive list possible. So we start off with, x to the n is n, x to the n minus 1, or x to the r here, n is a positive integer. Here, r is a real number, r x to the r minus 1. The next one that you might do is e to the x. Its derivative is just e to the x. If I give you b to the x, the derivative is a little bit harder. It is b to the x times the natural log of b. Now, one of the things that people often find annoying when they get to college is we no longer use log to denote the log base 10. Is in higher mathematics, we never really want to work with base 10. We always want to work with the natural log. And this is essentially the reason why. Because the derivative of e to the x is e to the x, but the derivative of b to the x is b to the x natural log of b, and you have to remember. If I give you the natural log of x, its derivative is 1 over x. If I give you the log base b of x, its derivative is 1 over x log base b of. I'm sorry. I'm sorry. It's x natural log of b. And so you have to remember those conversion factors. The other standard ones you want is the derivative of sine of x is cosine of x, and the derivative of cosine of x is negative sine of x. And the mnemonic I like to use is you have to remember where to put the minus sign. It's minus sine. You can also try to remember this by drawing a picture of the circle. So if we draw the unit circle, and if you are a little bit drunk, that looks like a circle. Here is some point. Here's my angle theta. Here's x comma y, which is cosine theta, sine theta. And you've got a couple of special points that you know. This is the point 1, 0. Here's the point 0, 1. Here's the point minus 1, 0. Here's the point 0, minus 1. If you look at what's going on over here, if theta is near 0, so theta near 0 and increasing, we see cosine of theta is going down, and we see the sine of theta is going up. So again, if I draw my picture, here's cosine theta down here, here's sine of theta up here. If theta starts off as small, when theta is 0, cosine is 1, and as theta starts to increase, the cosine is getting smaller. So if it's getting smaller, it turns out that means the derivative must be negative. And so this is one of the big interpretations of the derivative. The derivative gives us what's happening to the function. And that explains why we have the sign here. So let's talk about that a little bit more. So let's look at f prime of a is the limit as x goes to a of f of x minus f of a over x minus a, or the limit as h goes to 0, f of a plus h minus f of a over h. And so imagine, here I want to plot things, and here's the point A. Imagine f prime of a is greater than 0. What would it mean if f prime of a is greater than 0? Well, it means that as x gets closer and closer to a, or as h goes to 0, this ratio has to converge to a positive number. If it's a positive number, it's separated from 0. It might be 1 over quadrillion, but it's still a positive number. So let's just say, for the sake of argument, let's say it converges to 3. Well, if I go a little bit to the right of a, so h is positive, then the denominator is positive. If the whole limit is positive, then the numerator must be positive. So f of a plus h must be greater than f of a. So if h is greater than 0, if h is small, f of a plus h is greater than f of a. So that means the function is increasing to the right. So f is increasing to the right of a. And a similar analysis would show that it's decreasing to the left. So I would have to look something like this. So if my first derivative is positive at a point, I'm getting larger to the right, I'm getting smaller to the left. If my first derivative was negative, then I would be getting larger if I walk to the left and smaller if I go to the right. So when I look back to what's going on with sine and cosine, cosine, if I start off at theta equals 0, cosine of 0 is 1. As theta increases, cosine is getting smaller. That means cosine must be decreasing. So that means the derivative of cosine must be negative. So that's why I have to have the minus sign, because sine of x is going to be positive when x is a small angle. It turns out that it takes some work to prove these derivatives. So right now I'm not going to prove these derivatives. So I'll circle back to them a little bit later in the lecture. This is big broad overview. So we have this wonderful interpretation of what the derivative means. If the first derivative is positive, we're increasing in one direction, decreasing in the other. So we can actually use this for optimizations. So let's say we want to find local max or min for a function f. And so say we have a function defined on some interval a, b. What I can do is I can say, well, look, if my function is differentiable, if my derivative isn't 0, I can't be at a max or a minimum. Because if my derivative is not 0, then just let me go a little bit further and I'd be either increasing or decreasing. Unless you're at the endpoint. And this will not go, well, I'll see if I can do this. So I'll try to stop the share. And so what I want to do now, let's see. All right, so the question is, where is my speed fastest? So the point of that is that my speed was fastest not at an interior point, but at an endpoint. And so when you're trying to find maximum minima, it's not enough to check for where the first derivative is 0. Where the first derivative is 0 gives you candidate points. And the candidate points are extremely valuable, but it's not enough. So the candidates are the endpoints. So say f of a, f of b, and then the critical points. So these are x such that f prime of x equals 0. So if you look at the places where the first derivative is 0, those turn out to be candidates for maximum and minimum. And so the hope is that you can find these points and that there aren't too many of them, and then you can use this to try to find optimal values of your functions. So what we're seeing from this is that it's very useful to be able to calculate derivatives. So, we just had as an application, this gives you a chance to find how do you maximize something, how do you minimize something. Now you could ask, how do I know if I'm at a maximum or a minimum? If the first derivative is 0, I'm a candidate, but is it a maximum or is it a minimum? So what I always like to do is, there's the second derivative test and there's the first derivative test. So first derivative test. So let's say, here's x, and let's plot below it f prime of x. And we have some point A, and let's say the first derivative is 0 here. And let's say the function is positive to the right. So that means I'm increasing if I go to the right. And then let's say it's negative to the left, which means as I approach from the left, my function is getting smaller. So just by looking at this plot, I need a function that's going to be decreasing as I come to A and then increasing once I get past A. So it's going to look something like this. So it's going to be a minimum. If it was the other way, if it was positive, if it was the other way, if it was plus, 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 0, minus, 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 that'd be a maximum. So one way to tell if you have a maximum or minimum is to just look at the sign of the derivative to the left and the right. If your function is twice differentiable, which means just take the derivative of the derivative, you have the second derivative test. And so if f prime of A equals 0 and f double prime of A is greater than 0, it's a minimum. And if f double prime of A is less than 0, it's a maximum. So the way to quickly see this is, let's look at two special functions. F of x is x squared and negative x squared. And so f prime of x would be 2x. F double prime of x, the derivative would just be 2. Here, f prime of x would be negative 2x. F double prime of x would be negative 2. So both have 0 as a critical point. But here, f double prime of 0 is positive. Here, f double prime of 0 is negative. This is a max. This is a min. And this is a really good general theme of mathematics. If you can often remember something approximately, but you can't remember it completely, just do a special case. And then that's enough to crystallize. So I know something is going on. And so let me just check with the simple parabolas x squared and negative x squared. With x squared, I clearly have a minimum. With negative x squared, I clearly have a maximum. Oh, okay. X squared, that parabola, f double prime of 0 is positive. Okay, so if the second derivative is greater than 0, it's probably going to be a minimum. There is a joke, almost certainly false, that when they were building the stealth fighter and the stealth bomber, they were trying to maximize stealthiness, and they found the critical value, but they didn't check to see if they found a maximum or minimum. And according to the joke, which is almost surely not true, they built the we're here plane. Yeah, doubt it's true, but all right. So we've talked about applications of derivatives. We've talked about how to find the derivative of x to the n. I've mentioned derivatives of other things, but there's infinitely many functions I could give you. So a lot of calculus is developing rules so that basically you take a big problem and you break it up into lots of smaller problems, and you have these rules for derivatives. And by understanding these rules, I actually can't give you any derivative that is beyond your ability. As long as it's made up of combinations of these simple functions, you can get it. You may not like doing it, you may curse me, but you can do it. Integration, completely different. It is very hard to integrate functions. Very few functions have closed form integrals. Integrals is the opposite of derivatives. So we have lots of rules. rules for derivatives. So the first is the constant. If I have c f of x and I want its derivative, it's just c times the derivative of x. So if you think about it, if I measure my speed in yards, which would be a stupid thing to do, but let's say I measure my distance in yards. If I now start measuring my distance in feet, the numerical value of my speed will be 3 times as much because there are 3 feet in a yard. My actual speed hasn't changed on an objective scale, but when I use these new units, it's going to look like I'm traveling at 3 times the speed before. And if you think about it, if I just multiply by c, I'm just changing the numerator by a factor of c. The next is the sum difference rule. If I have f of x plus g of x, the derivative of that is just f of x plus g of x prime. And similarly, if I have their difference, the derivative of a difference is the difference of the derivatives. Which makes sense. If at every moment in time I'm f of x units from home and another one I'm g of x from home, and then I add them together, it's like I'm traveling the 2 speeds together. The more complicated one is the product. If I have f of x times g of x, the derivative is f prime of x g of x plus f of x g prime of x. And when I teach calculus, I actually go through and discuss how you could actually guess that this is the right form. And what you can do is you can look at special cases. If you try f of x is x to the n and g of x is x to the m, this is the only way that will combine nicely. So if you know a couple things you can deduce. We have quotient. So if I have f of x divided by g of x, we have f prime of x g of x minus f of x g prime of x over g of x squared. And so this is the quotient rule. Now we still have a few more advanced rules. And we're not talking today about proofs, we're just trying to give a quick introduction. We have the chain rule. If we have f of g of x and we ask for its derivative, it's f prime at g of x times g prime of x. So whenever you hear of, you should think the chain rule. And this g prime of x is the most forgotten item. So for example, if I give you f of g of x is x to the n, so its derivative is n x to the n minus 1 times the derivative of x. What's the derivative of x? It's just 1. And so when you look at the special case of g of x equals x, it actually reduces to what we've already seen, which is good. But you don't see that extra g prime of x term because it's just 1. And again, it's one of the most forgotten things. This has as a nice corollary the power rule. If I have f of x to the nth power, its derivative is n f of x to the n minus 1 f prime of x. And we also have the multiple rule. If I give you f of c of x and ask for its derivative, it's c times f of c of x. Or really, I'm sorry, f prime of c of x. It's really f prime of c of x times c, because it's just the special case g of x equals x. So you can now handle any derivative by using this. So for example, let's say I give you, a of x is 3x squared e to the 2x squared plus 5x. And I want to calculate its derivative. So a prime of x, well, the first thing I would do is I would do the sum rule. The derivative of a sum is the sum of the derivatives. Then I would do a product rule. And so if I want to do the the product rule, I'll wait for just a second, because the derivative of 5x is just 5. So if I want to do the product rule, it's very easy for me to do this because I've been doing this for longer than you've been alive. If you haven't done it too often, what you might do is say, let's let f of x be 3x squared, g of x be e to the 2x squared, f prime of x is going to be 6x, and g prime of x, okay, e to the 2x squared, that's not a function I know immediately. I'm going to just hold off on that for now. And then f of x, g of x prime is f prime of x, g of x plus f of x, g prime of x. This takes more time to write it like this, but by doing it like this, I've got everything in front of me, and it makes it very easy for me to just substitute in. So now I have a prime of x is f prime g, so it's going to be 6x e to the 2x squared plus 3x squared, and then I've got g prime of x plus 5. And so now all I have to do is figure out what is g prime of x. All right, g prime of x will have e to the 2x squared. So g of x is e to the 2x squared. So I can write this as exponential of 2x squared. When I write it like that, exponential of, I'm hearing the of, this is a chain rule. So I can write this very slowly as b of c of x. And let's identify everything. So my c of x is going to be the 2x squared. My b of x is going to be e to the x. And you see that if I put in c of x with my input, my rule is b of input is the exponential of the input, e to the input. So when I put in the input, I will get e to the 2x squared. C prime of x is just going to be 4x. B prime of x is just e to the x, derivative of e to the x is e to the x. But I want b prime not at x, but at c of x. So that's going to be e to the 2x squared. And now I do, g prime of x is b prime of c of x times c prime of x. So g prime of x is going to be e to the 2x squared times 4x. And so this is how you would use these differentiation rules to take something complicated and break it up into lots of smaller pieces. All right, so some of the big theorems that we want is we have the triple letter theorems. We have the intermediate value theorem. And what this says is if f is continuous on the interval AB, then for any big C between f of A and f of B, we have a little c in the interval AB such that f of little c equals big C. And so, again, if my function here's f of A, here's f of B, and I know these two values, you give me any value between them, then if I have a continuous function, I can't get from f of A to f of B without crossing that line and equaling it somewhere. Now, I could actually go lower, I could overshoot, I could hit it multiple times. That's fine. I'm not saying that it's never larger than f of B. I'm not saying it's never smaller than f of A. I'm just saying it has to hit at least once. So this is the intermediate value theorem. One of the consequences of the intermediate value theorem is the mean value theorem. Mean value theorem. So if f is continuous and differentiable on the interval AB, there is a C in AB such that f prime of C is f of B minus f of A over B minus A. so that at some point in time, your instantaneous speed equals your average speed. So there could be multiple points where that happens. So maybe here's A, here's B. Here's the line connecting them. And then in this case, it looks like I'm going to have 2 points where my instantaneous speed has that same slope. So this is an extremely valuable theorem. And this is similar to how we were approximating the function. We use stuff like this to form what's called Taylor series. And the idea or the hope is that f of x should be given by approximately f at a plus f prime of a x minus a plus f double prime at a over 2 factorial x minus a squared plus f triple prime of a over 3 factorial x minus a cubed, and so on and so on and so on. And we choose this such that if we take the derivative, well, let's see, if we first take x to be a, then the only term that survives on the right is f of a. So we'll call this right-hand side the Taylor series of f. So Tf of x. I'm running out of room there, so. So we'll call it the Taylor series at x. So note, the Taylor series at a is just f of a. If we take the derivative of the Taylor series at a, we get f prime of a. And the reason is if you have the x minus a squared, its derivative is going to be 2x minus a. And when you then put in x equals a, it vanishes. If you look at x minus a cubed, if you take its derivative, it's going to be 3x minus a squared. When you put in a, the only term that survives is x minus a, whose derivative is 1. And this is why we have the factorials down below. So it's a good calculation to do. If we take 2 derivatives, we get f double prime of a. So the whole point is that this function, this infinite sum, is supposed to approximate our function. And the more terms we take, the better approximation it should be. A couple of key famous ones, and sometimes these are used as the definitions. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot 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 is the sum, and goes from 0 to infinity, of x to the n over n factorial. And this symbol means sum. It means take what you have next to it, the x to the n over n, and replace n with 0, with 1, with 2, with 3, and add. Related to this, you have cosine of x is going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on and so on and so on. If you look at these, you should see there seems to be some similarity between e to the x and cosine and sine. And it turns out e to the ix is cosine x plus I sine x, where here I is the square root of -1. As this is meant to be just a 1-hour introduction, I am really not worrying at all about proving things rigorously. You're proving that these sums converge. But this is a wonderful result. And in fact, this is the secret of where all of these identities come from. Why is the derivative of cosine sine? Why do we have angle addition formulas? It all comes from the exponential. Now, it turns out that if I give you e to the x times e to the y, you would say, well, of course, this is e to the x plus y. That has to be proved. Technically, this is the sum as n goes from 0 to infinity of x to the n over n factorial. That's technically what e to the x is. Technically, e to the y would be m goes from 0 to infinity, y to the m over m factorial. And then you're saying that this is equal to the sum, say, k goes from 0 to infinity of x plus y to the k over k factorial. So the proof is basically the binomial theorem. And reorder sums. So if you reorder sums and you use the binomial theorem, it justifies this notation. If this were not the case, then this would be horrible notation, because when you see e to the x, you think x powers of e. But what does it mean to raise e to the square root of 2's power? I understand what x squared is. That means x times x cubed, x times x times x. X to the 1/2, okay, I'm looking for a number y such that y times y is x. I can understand integer powers, I can understand rational powers. What does it mean to take something to the root 2th power? Well, e to the x makes sense for any x, because you're just raising the x's to an integer, dividing by n factorial, and then adding. So how does this help us? Well, let's look at e to the ix times e to the minus ix. That should just be e to the 0, which is 1. E to the ix is cosine x plus I sine x. E to the minus ix is cosine x plus, it's cosine of negative x. Well, cosine of negative x is cosine x, plus I sine of negative x. Sine of negative x is negative sine of x. So just cosine x minus I sine x. Oh, well, cosine times cosine, that's cosine squared x. I sine x cosine x minus I sine x, that cancels. Then you have a plus I sine x times a minus I sine x. That's going to be a minus I squared. I squared is -1, so that's going to be plus sine squared. There's Pythagoras. The next one is if I give you e to the ix, e to the iy, this is e to the ix plus y. So cosine x plus I sine x times cosine x, cosine y plus I sine y is cosine x plus y plus I sine x plus y. So if I have two complex numbers, the only way they can be equal is if the real part equals the real part and the imaginary part equals the imaginary part. So I would get the real part is cosine x cosine y minus sine x sine y is cosine x plus y. And then I would get sine x cosine y plus cosine x sine y is sine of x plus y. There's my angle addition formulas. They all come from the exponential function. So there's a bunch of other stuff that you can do in Calc 1. A lot of Calc 1 courses, they do have the fundamental theorem of integration mentioned in. I'm going to do that in the Calc 2 review. You can talk about solving some differential equations. I'll put that in the Calc 2 review. The main stuff we did here was we talked about what are the key derivatives. How do we use the rules of differentiation to take a complicated expression, make it easier? We talked about the key theorems. So we have the mean value theorem, the intermediate value theorem. We talked about what does the first derivative mean. If the first derivative is positive, you're increasing to the right, decreasing to the left. The first derivative being 0, this is a great way to find candidates for extrema, for maxima and minima. And then, the real thing is, what do you apply this to? So there's a lot of different problems that you can apply this to. And again, 1 hour introduction, we're not going to be able to get into all that. This is just high level. So I've got about 1 minute left, so I'm going to use the last minute to just give one proof. So let's look at the product rule. And so I'll first do the intuition. Let's say we take f of x is x to the n, g of x is x to the m, and then a of x is f of x, g of x is x to the n plus m. These are great ones to choose because we know the derivative of each. Do you have like 2 or 3 minutes? Okay, because I saw it just a little bit late. So I know f prime of x is just n x to the n minus 1. G prime of x is m x to the m minus 1. A prime of x is n plus m x to the n plus m minus 1. And so now my question is, looking at f prime, g prime, is there a way to combine them to get a prime of x? And after a little bit of inspection, you see that f prime of x g of x plus f of x g prime of x is a prime of x. This is not a proof, but this is a way to see that this is a reasonable thing to try to prove. As another example, you could do f of x is cosine x, g of x is sine of x, and then a of x, cosine x sine of x, is actually 1/2 sine of 2x. So if you're really good, you could actually use this to give you a second data point. Now, as a warning, I want to test algebra. What is 16 divided by 64 in lowest terms? 1/4, 19/95. Nope, 19/95. 1/5. 49/98. So 49/98. 1/2, right? 1/2. And 12/24. No, 12/24 is 1/4. Yeah, I'll show my work. 19/95, I'm sorry, 16/64, cancel the 6's and you get 1/4. Cancel the 9's, you get 1/5. Cancel the 9's here, you get 4/8, which is 1/2. So clearly, no, just because it works a few times does not mean it's going to work in general. And so you have to be very careful. It's not bad to gain some insights. So the quick proof, we're going to end after this. So here's the proof. So a of x is f of x, g of x. So all of the proofs start the same. They start with the definition of the derivative. It's the limit as h goes to 0 of a of x plus h minus a of x over h. So step one of every proof is you write the definition. Step two is you substitute. And I'm going to substitute intelligently because I've done this for 20 years. It's f of x plus h, g of x plus h, minus f of x, g of x over h. And you'll notice I've left a huge space. And the reason I've left a huge space is we're going to do nothing. We're going to add 0, and we're going to add 0 in such a way that it's going to be great. Well, I believe from what I've just seen that the answer should involve something like f prime times g. I've got an f of x plus h, g of x. Well, if I want to get an f prime, I would want an f of x plus h minus f of x. So I'm going to subtract off f of x, g of x plus h. And since I subtracted it, I have to add it back in immediately, f of x, g of x plus h. And why am I going to do this? Well, now this is the limit as h goes to 0, f of x plus h minus f of x over h times g of x plus h plus f of x, and the next one will be g of x plus h minus g of x over h. And now we just use limit properties up the wazoo. If everything is nice, the limit of a sum is the sum of a limit. The limit of a product is the product of the limits. As h goes to 0, this is going to go to f of x. This is going to go to g prime of x by the definition of the derivative. G of x plus h is just going to go to g of x as h goes to 0. And this is just going to go to f prime of x. And we put the little square box for QED, that which was to be proven, to show that we've reached the end. So this is how you would prove one of the results. The sum rule is even easier. The chain rule is harder. So the chain rule is the one that's really hard. All right, so this is a good place to stop. Any questions? So this is, all right, so this is the 1 hour quick review of Calc 1. There's a lot of practice problems if anybody wants to try to do the practice problems. That's really how you get things done. But at a high level, this is what's going on. And the danger is just being aware of when have they slipped things past you. So again, we know that dividing and canceling like this is bullshit. Oh, now this is no longer available for kids. Oh well. We know you can't just cancel the 6's. We know that's illegal. But there are other things which it's harder to tell. E to the x times e to the y is e to the x plus y. Why is that true? Well, you have to go back to how we defined e to the x. When we calculated the derivative of x to the n, we assumed n was an integer because we were using the binomial theorem. So it's very easy to make some small, subtle mistakes. I'm going to stop recording.